Yo, yo, what's up? This is the Grandmaster C. You see me as such fine quality chemistry educational videos as, oh gosh, I blew up the lab again and dropped that base into another beaker of acid. Today I want to give an introduction, a little bit, into acids and bases for AP Chemistry. We're going to look at some basic foundations for this in the time that we have. And in chemistry, when you're looking at acids and bases, there's a couple of ways of defining what acids and bases do. So there's Arrhenius, the Swedish chemist, who came up with some pretty cool ideas, like activation energy. And you also had a team, Bronsted-Lowry. They also worked with acids and bases, and they do have different definitions. So we're going to look at our basic acid and base foundations. On Arrhenius acid and Arrhenius base, they are releasers. They give something. And an Arrhenius acid is a hydrogen releaser. It gives off hydrogen ions. You could look at that as protons, that they release protons because hydrogen pretty much is a single proton. Usually it doesn't have its electron. Now there are hydrogen atoms that do have a neutron connected to the proton in the nucleus of the atom, but usually, the vast majority of the time, hydrogen is just a single proton. Now, an Arrhenius base, on the other end, is a hydroxide releaser. Okay, it gives off these OH minus. Okay, and then Bronsted-Lowry, or we'll just say Bronsted. A Bronsted acid is a hydrogen donator, a proton donor, if you will, and a Bronsted base is a proton acceptor. Now, I do want to point out something. If we look at something like ammonia, NH3, well, according to the Arrhenius base, it's not an OH releaser, so according to Arrhenius, NH3, ammonia, would not be a base. But, according to the Bronsted definition of the base, it does accept the proton to become NH4, which is ammonium. So that's why we have the two different definitions about that. And this is a very quick definition of acids and bases. So typically I go with a proton donor, a proton receiver. Okay, that's what I pretty much go with. Now, we need to talk about conjugate acid and conjugate base, because that is something in any chemistry equation we're going to need to understand that acids, when they donate their hydrogens, they do get picked up by somebody in the other side, in the product. Bases, on the other hand, they're going to receive hydrogens on the other side as well. So, a conjugate acid, within the Bronsted-Lowry acid-base theory, it's a species formed by the reception of the proton by a base. In other words, the base has a hydrogen ion added to it. So if we look at an equation like NH3, we know that as a base, but if it picks up a hydrogen ion to become NH4, ammonium with a +1 charge, that would be considered a conjugate acid. Okay? Now, a conjugate base is formed by the removal of a proton from an acid. So the conjugate base of an acid is the acid that has the hydrogen ion removed, taken away from that. So how do we see that on a visual sense? Well, a conjugate acid of the base is a base plus the hydrogen. In other words, it picks it up. And then a conjugate base of the acid is an acid with the hydrogen losing that hydrogen ion. So here we got some examples here. Now, all of these are acids. Now, how would I know that they are acids? Well, one clue, if you look at these, you have hydrogens at the beginning, with the notable exception of NH4. Now, all those, when you see an H at the beginning of the formula, that's a clue that it's an acid. Why? Because you have a hydrogen ion that's going to be given away. Because that's what acids do. They donate protons. So, when we look at the conjugate base of HNO2, well, hey, it's an acid. It gives away the hydrogen. And guess what? It becomes NO2 with a -1 charge to it. That's the conjugate base of this. If we look at NH4 with a +1, Well, even though the hydrogen is not on the front like that, it still has a +1 charge. We can make that a conjugate base, and what that would be, it would be NH3. Okay, it loses it. It loses that. Okay? All right, let's move on. Well, actually, I definitely need to move on. So, what is the conjugate acid of Cl-1? Well, the conjugate acid of Cl with a -1 charge is HCl. A conjugate acid, remember, it picks up the hydrogen ion, just like OH-1 here. It picks up the hydrogen, and guess what? It becomes an H20. Wow, yeah, absolutely. Absolutely. Okay? Now, here we can go and look at an equation and identify which ones are acids and which ones are bases. What is the conjugate acid and the conjugate base? Well, if I didn't know this, and I looked at this, and for the sake of argument, we're going to assume they're balanced. Okay, here's an acid, here's a base. Now, why would I know that this is an acid? Because of that hydrogen ion there. It's an acid. Just like I look at this one here, this is my acid right here. Because I know it's going to give away the hydrogen ion. So I know here's my acid, here's my base. Now what do acids do? Acids give the hydrogen ion. So that's going to become from an HNO3, that becomes an NO3. Notice how it becomes an acid. When it changes, it becomes a conjugate base. That's the thing. And here's our base. It's going to pick up the hydrogen ion, and it becomes a conjugate acid. It becomes HPO4 with a -2. See, that's the difference. A base becomes a conjugate acid. An acid becomes a conjugate base. When you have an acid-base equilibria, that's coming into play here. Okay? So, given the time, I'm kind of paying attention to my time. I only have a couple of moments here. This is pretty self-explanatory. Number 9, what is amphiprotic? Well, here's something to think about. When you look at protic, the first thing that should come in your head is the H's, the hydrogen ions, the protons, protic, protons. So you hear diprotic, monoprotic, triprotic, protic. All those are telling you how many hydrogens does it give off as an acid, okay? And let's move on. We know about water. Water, the thing about water, ladies and gentlemen, is that water, if you look at a glass of water, guess what? It's not all 100% water. It's not all H2O, because water will break up. It will break up and form a hydroxide ion, an OH-, okay, which makes it a conjugate acid, and you have the H3O+, which becomes a conjugate base. Yeah, confusing, isn't it? You have to practice a little bit. So, the dissociation. Now, dissociation, that would be an important thing right here. Dissociation has to do with how much does it break up. Okay? So, if we look at strong acids and bases, they break up, they dissociate 100% completely. Then, you have, on the other side of the coin, what happens when you have a weak acid or a weak base? Now, a weak acid, great example, vinegar. Now, don't confuse vinegar's inability to dissolve in water that it won't hurt you. Concentrated vinegar, you pour it on your skin, you will go to the burn control center. Oh, my time is up. Well, okay, gave you some basics here about what's a Bronsted-Lowry acid and base, what was an Arrhenius base and acid, talked to you guys about conjugate acid, conjugate base, and talked a little bit about dissociation of strong acids and strong bases, as well as weak acids and weak bases. Hey, stay tuned, because I am going to do another one dealing with POH. Until then, Grandmaster C, out.